Hi everyone, this is Hardik from Fuzzing.in. Thank you for watching my videos. In our last few videos, we have seen various fuzzers on Linux as well as on Windows platform. We have seen various fuzzers like AFL, MAFL, libfuzzer, libAFL, home fuzz, etc. So far, we have been using a very common CPU architecture, that is x86 or x64, and we used to compile our binary for this platform, and we used to fuzz that. But as you know, there are different CPU architecture like ARM or MIPS. So in this video, we are going to see how can we compile our DAM vulnerable C program for different architecture like ARM or MIPS, and what kind of toolchain we will need to be able to compile our DAM vulnerable C program for these different platforms. And then we will see how can we fuzz these different platform binaries in Qemu mode using AFL. So let's start. So if you are new to my channel, then I will quickly go through our DAM vulnerable program. If you are watching my videos, if you have watched my previous videos, then you can probably skip this part. So this is a very simple program which I have coded to explain various fuzzing concepts, and it has a lot of vulnerabilities. So basically, it is an imaginary image file, you can say, which has the specific format. There is actually a header which is of 4 bytes. There is an integer value which is width, the integer value which is height, and there are some data, 10 bytes. So this is a structure, and this structure will be saved to our image file. And then what this program will do, there is a function that is process image function. So this function will open the provided input file, assuming that this is the image file which follows this structure, and then it will read the data in that structure, and then it will perform various operations, like it will add width and height, and it will allocate some memory based on that, and it will try to copy some data like image data to this memory location. And there are a lot of vulnerabilities, like there can be heap buffer overflow, there is integer overflow, there is use after free, there is double free, there is divide by zero, there is out of bound read writing, as well as in the stack buffer, and there is memory leaks, there are stack exhaustion, etc. So I'll be giving the link to this program in the description section of my YouTube video. You can go and you can git clone and you can play with this. And with this, if you are interested in knowing more about this program, I will request you to go to my previous video. I explained this program in detail. So for this video, I think this is enough. Now, first thing we need to do is that we need to install ARM and MIPS toolchain so that we can compile our DAM vulnerable program for an architecture. Now, if for example, if we simply use GCC to compile our image read program, then by default it will compile it for x86 64. This is actually a 64-bit binary, and it is an ELF file, as you can see. This program will not run on other architecture. So for that, we need to install ARM and MIPS toolchain. So let's see how can we install ARM and MIPS toolchain first, and then how can we compile this program architecture. Let's see. To install ARM toolchain, basically what it will do is that it will install various compiler, various required libraries, and various tools to enable the ARM platform compilation for provided C program. So for that, you can run this command, that is sudo apt install gcc, then make gcc arm linux gnu abi, utils arm linux gnu abi. What this will do is that it will install all the required dependencies to compile our program for ARM architecture. And similarly, if we want to install cross-platform compilation for MIPS, then we need to install those toolchain. And for that, we need to run this command, that is, this is the command which will install GCC for MIPS, this architecture. So in my case, I have installed this both. And one more thing to notice is that the ARM compiler which we have installed is for 32-bit binary. If we want to compile 64-bit binary, then we need to install another package, and that is this one. So you need to run this command, that is sudo apt install gcc make and gcc ar64-linux-gnu and binutils-ar64-linux-gnu. So what this will do is that this will install ARM toolchain, compile 64-bit ARM binaries. The toolchain which we installed previously, that is gcc-arm-linux-gnu, this is for 32-bit binaries. So once you have installed this, you can easily compile your binary for ARM as well as for MIPS architecture. It is straightforward. And what this toolchain will do is that they will provide you various GCC compiler, like in this case ARM-linux-gnu ebi.gcc. So by using this, you can compile your program for 32-bit ARM platform. And if you want to compile 64-bit, then you can actually use AR64-gnu GCC compiler. Will compile 64-bit ARM binaries. Similarly, if you want to compile your program for MIPS architecture, then you need to use MIPS Linux GNU GCC compiler. This will basically create 32-bit binary for MIPS architecture. Now let us go ahead and compile imgread.c file first for ARM architecture, and then we will see how can we execute. So to compile this in for ARM architecture, we can simply use gcc. So this is the command, that is arm-linux-gnu abi test. This is the source file, that is imgread.c-o, that is the output file name, and let's call it ARM. You can see that it has actually read our terminal C program, and there is an ARM binary. You can see it over here. This is the architecture, that is ARM, this EAPI version, and it is a 32-bit binary. Now similarly, we will go ahead and we will actually use AR compile 64-bit ARM binary, and let's. So you will notice that it is actually a 64-bit binary, which is for ARM 64-bit architecture. As you can see it over here, 64, there is ARM only, and this is 32-bit, this is 64-bit. So we have two ARM binaries. Now for this to run, you need AFL with Qemu mode installed. If you have not installed AFL Qemu mode, then I will suggest you to go and watch my previous videos where I have mentioned how can we install AFLPlusPlus on your system. And if you have not installed, if you want to install, then you can simply go to your AFLPlusPlus directory. You can go to Qemu mode, and inside Qemu mode you will see that there is a file called build Qemu support.sh. Now what this file will do is that it will download, it will compile Qemu for a specific CPU architecture. So in our case, if you want to run ARM binary using Qemu, then you need to provide CPU architecture ARM. If you want to run MIPS binary, then you need to give CPU architecture as MIPS. So there is a hack which is provided by Dominic, thanks to that. And what he suggests is that once we run the script, like with CPU architecture, we need to use this command, that is CPU target is IPS, or it can be ARM, or it can be x86, or it can be x86 64. And once we run this, what this script will do is that it will basically compile Qemu for the specific architecture. In this case, we have given CPU target as MIPS, so it will build Qemu with MIPS support, and it will actually create one file, that is AFL Qemu trace. That is actually the compiled version of Qemu. And what we can do is that we can save this file with different fixes like AFL Qemu trace, ARM AFL Qemu trace, MIPS is x86 before, so that we don't need to compile this every time. Let's wait till the compilation finish and stop this video, start it again. Then we will discuss one. So you can see that it has compiled our binary, and what it will do is that it will actually, so this is the binary which this is actually the Qemu, compiled Qemu, and it actually has various options. So for every CPU target, every different architecture, we need to have this file so that we can fuzz that file using Qemu with AFL. What we are going to do now is that since this is for MIPS, means this can only run MIPS files. What we will do is that we will copy this as into our user local bin as AFL Qemu base -MIPS. Now what this will do is that we can actually use AFL to fuzz MIPS binary with Qemu mode. Now similarly, if we need to compile or if we need to fuzz ARM architecture, and what we will do is that we will use CPU target as ARM, and we will again run the script. So this step you need to run on only one time till you get this different AFL Qemu trace -MIPS or AFL Qemu trace -ARM binaries, and save it to user local bin directory, and then you can use AFL to fuzz various architectures. So to do this step for every architecture you want to fuzz. Please note this point. You need to do this step. You need to run this build Qemu support shell script for every CPU target or architecture you want to fuzz. So if you want to fuzz ARM, you have to run it for ARM, and if you want to fuzz MIPS, run this for MIPS, and then you can save this file. So now let's run it for ARM. Again, wait for the compilation to finish. Okay, so you can see that compilation has been finished, and there is one file that is AFL-Qemu-trace has been created. Now this file is actually the modified Qemu, and it is specifically compiled for the ARM architecture. So now again we will do the same step. We will copy AFL Qemu trace to our user local bin with a different prefix, that is ARM. So this is a compiled Qemu, is a modified version of Qemu which is specifically used to run ARM based binary. So we'll simply copy that, and with that we will now see how can we run our program first on the Linux based system, and then we will see how can we fuzz it. Let's start. Now as you can see, we have compiled our damnable C program for ARM architecture, and this is the file output. File command on this will give us different information about the compiled binary. So it is a 32-bit binary for ARM architecture, and now let's see if we can run this binary on Linux or not. We'll simply try running that. And you will see that it is not able to run, although I have Qemu installed on my system, and it is complaining about one file, that is -lib nd-linux. So it is missing some dependencies, and for that what we can do is that we can simply locate this file, and we will figure out where it is present. So you will notice that it is present in the ARM-linux-Qemu ABI. So this is the path which we actually need to provide to our program if you want to run it. So what we can do is that we can use AFL Qemu trace, actually give this path to the ABI, and then we can run our ARM. Okay, so you can see that our ARM binary is working over here, it's running here, and is throwing this message that cannot open file or file doesn't. So since this was a non-static binary, it means that it will require some dependencies, some libraries or some common functionalities, and we need to specifically provide this path. So we can use AFL Qemu trace which we have compiled for ARM architecture, and we need to use this option, that is -l, that is the library which is over here, and then we can provide our file name. So this way you can run non-static binary. Now to avoid these issues, what you can do is that you can actually compile your binary in static mode as well. So let's see how can we compile this. For so you simply need to add dash static while compiling this file, and what it will do is that it will basically create one statically linked file. So it will basically not look for all the dependency, it will have all the code in that executable file itself. So now let's compile it. Remember the command, that is arm-linux-gnu-api-c. We are compiling a 32-bit ARM binary. Then our program file, that is c.c-4, and I have given the name is ARM and static, so be clear that it is a statically compiled ARM binary. And let's run. So now what you can do is that you can simply run this file, say img read arm_static, and it will work without any issues. Basically what happens behind the scene is that since we have Qemu installed, it will be actually executed by and not by the Linux system over. And similarly we can actually generate MIPS binary as well. So let's create MIPS. First what we can do is that we can try running our MIPS binary, see if it works. So as you can see that it is again complaining about some missing library, so we can again do allocate file.so.1, and you will notice that it present inside this directory, that is user MIPS Linux. So we actually need to provide this path, but there is a catch. We cannot run it with ARM architecture, right? If you give this command, it will not work. Yes. So you will get a message that is invalid ELF image for this architecture. So this is the reason that we need to run Qemu support tool for every different architecture, because once you run that script, that will be bind to that specific architecture. You cannot run any other architecture. Now in our case, since we have run that script, that is build Qemu.h for MIPS architecture, and it has generated a AFL-Qemu is for MIPS as well. What we can do is that we can simply use that to run our MIPS compiled binary. And now let's see what happens. You can see that our program is working over here. It is showing the error message, cannot open file or file doesn't exist. So I hope that this clarifies the doubt that why you need to run build Qemu support for every architecture. So you will get separate file which you can save it, and then you can use that. And this actually makes fuzzing very easy. I mean, once you compile and install this different AFL Qemu traits for ARM and for MIPS and for x86 and all other kind of stuff, you can simply use file and with AFL and easily fuzz binaries. So now let us go ahead and see how can we fuzz ARM binary with AFL. For that, it is actually very simple now. So we have created one simple input file. We have one directory that is in. So let me show you. If we go inside in, there is one.imp. This is a sample image file. I will again suggest you to go to my previous video. If you are not familiar with what I am doing over here, you will see that this is a simple input file, seed file, which contains img tag over here. So we will provide this to the fuzzer, then we will fuzz it. So now the command which we can use to fuzz is the AFL fuzz. Then we need to use it, and then that type, that is our input directory -o, that is our output directory. So let's name it to ARM --. Then we need to specifically specify AFL Qemu trace over here, because we have different version of AFL Qemu trace. So in case we want to use _ARM, we use underscore, but because I use dash, so it's okay. And then we also need to give our library file. That file is non-static, so that is using shared library. We need to give the path, otherwise this option is not needed over here. So let's give that is ARM, maybe dot slash read and ARM. Okay. And let's see if it works. Okay, so as you can see, it has started fuzzing our ARM binary. It has found one crash and we are getting decent speed over here. So ultimately our RAM vulnerable C program or imgread.c program, which we have compiled for ARM architecture, we are able to fuzz that on a Linux, as you can see it over here. And now I'm going to cancel the fuzzing this and we will try to replicate the crash. So again, we need to use AFL Qemu trace and then we can actually provide our input file which is causing crash over here. We will try to see if it crashes or not. We have one and let's see what this path was wrong. Correct. Okay. And you can see there is a segmentation fault over, and if you do root cause analysis, you will see that there is image width and image height which is very large value, that is major overflow, and that is causing all the problem. That is the that will be the root cause of this issue. I'm not going into much detail over here. So we are actually able to fuzz ARM binary in AFL in Qemu mode, based system, and this is kind of interesting. Now let us go ahead and see if we can fuzz MIPS binary as well. So we have already generated our MIPS binary for variable C program. We already know the command AFL -fuzz -u -i put that in -o out. Let's call it MIPS -AFL Qemu trace and -MIPS -l, and we need to give MI library here and compile MIPS binary. So this is our MIPS binary, and let's see if it works. Okay, so you can see that this is quite MIPS binary which we are fuzzing using Qemu mode Linux based system, and let's wait for a few seconds, take or so till it finds first crash, and try replicating that crash. It might take few seconds. Okay, we just got our first crash. So now I'm going to cancel the fuzzy campaign over here. Let us again try to replicate our crash. So remember that we are MIPS binary here, so the MIPS, and we need to give MIPS library. Okay, again we need to use MIPS binary, and we need to change the out score MIP for crash hit. Right. So there is a segmentation fault over, and again the same root cause likely will be there, width and it's too big, and that might not suck. So in this way you can actually fuzz various picture in AFL on a system. And now one more thing, if you want to fuzz static binary, then you don't need to give this path which we are giving over here. So what we can do, that show you, can actually remove this, all that static, and run it. You will see that it will work without any fine within few seconds. It also, you will notice that we are getting pretty decent speed over here. Okay, so you can see that found one crash after a minute seconds, and I'm going to cancel this. So if you want to run static binaries, you don't need to give the library path. So you can simply run that in AFL trace. Now simply run it nonstatic. You can see that it is running. You don't need to use -l option here to library on files. So in this way, you can actually fuzz different picture binary AFL on Linux demo mode. I hope that you enjoyed this video. Feel free to subscribe, like, and share my channel. That will motivate me to get more such videos. If you have any questions, comments, or feel free to post in the comments. Feel free to read Twitter. And till the next video, stay safe, enjoy.